Hi, welcome to Unacademy. Unacademy is the India's largest online learning platform. So I am welcoming you all to this beautiful online learning platform. Happy learning to all. Now we are happy to announce that Unacademy is going to providing classes to GATE and engineering service examinations. The engineering students who are appearing for GATE and engineering service, for them now Unacademy is providing classes from India's top educators. Okay, now about myself, I G Venkata. I have 16 plus years of teaching experience. So far, I mentored more than 60,000 students for their GATE examination. At present, I am doing my PhD from JNTU Kakinada, and my specialization is VLSI design. Now, first we check how to get the Unacademy learning app into our device. Just go to Play Store in your device. Now in that type Unacademy in that. After that, just click this button install, then it will install Unacademy learning app into your device. Once you open that app in your device, it will shows what are the different courses available in that, and in each course who are the top educators handling different subjects in that course. Okay, it will give that information. At the same time, you have one more option. Now about that educators, introductory video also you will get. So you will get a brief information about that educator. Okay, that facility is available here. Now we are happy to announce that 2 new batches are going to start. See, just here you can see few of the top educators. Tiwari sir, he is the IIT topper. Ankit Goyal sir, he is the All India topper 2 times in electrical gate. Jaspal Singh sir, he is the All India 4th rank in IS. He is ex-IS officer. Okay. And Jain sir, okay, he is having a vast experience in computer science and engineering. And here are the few of the top educators from Unacademy. Now we are happy to announce to introduce a new batches for GATE 2022 and GATE 2023 students. Now there is a Ascend batch for GATE 2023 in mechanical engineering. This batch started from 8th February 2021. Okay, and here are the top educators who are handling the subjects in that mechanical. Now there is a Evolve batch for GATE 2022. Okay, the same team is going to be taking the classes for mechanical students for Evolve batch GATE 2022 also. Now this batch started from 8th February 2021, and don't forget to use my code during subscription VRAW10. VRAW10, don't forget to use to get 10% discount. Okay, next there is a Ascend batch for GATE 2023. This time this is for civil engineering. Okay, now it is the team and taking the classes for civil engineering, and this batch started from 8th February 2021. And there is a Evolve batch for GATE 2022 civil engineering. This batch started from 8th February 2021. Next we are moving to computer science and information technology. There is a Evolve batch for GATE 2022. It is the computer science and information technology team. Okay, these are the top faculty handling the classes for computer science and information technology students. This batch started from 8th February 2021. Next there is a Ascend batch for GATE 2023 electrical engineering. Okay, here is the top educators who are available, who are taking the classes for electrical engineering. Okay, Now, this batch started from 1st February 2021. This is GATE 23. Again, there is a GATE 22. Now, there is a GATE 2023 Ascent batch. For this time, it is for Electronics and Communication Engineering. This batch started from 1st February 2021. And there is a eval batch for GATE 2022. Again, it is for Electrical Engineering. The same team who are handle the class for GATE 2023, same team is going to taking the classes for GATE 2022 also. Okay, this batch started from 1st February 2021, and there is a eval batch for GATE 2022. This time this is for Electronics and Communication Engineering. Okay, it is the here are the top faculty who are handling the classes for Electronics and Communication Engineering. Okay, this batch is going to start from 1st February 2021. Now we are moving to Chemical Engineering Department. So any of your friends are in Chemical Engineering side, please inform this one to them, because at outside it is not possible to get the training for Chemical Engineering. Very rare locations they get this training, but for the students who are doing the Chemical Engineering, for them it is very difficult to move from their location to that point. Okay, now they must thank to Unacademy to provide such a beautiful provision to them. By gathering all the top faculty in computer science, chemical engineering, okay, they are providing training to them. This is for GATE 2022 eval batch. This batch started from 25th January 2021. And don't forget to use my code VRAW10 during subscription to get 10% off discount. Okay, and here are the different courses which are provided by Unacademy for GATE and service examinations: mechanical engineering, electrical engineering, civil engineering, production and industrial, instrumentation engineering, chemical engineering, electronics and communication engineering, and computer science and IT departments. Okay, these are the different courses providing by Unacademy. Now, there are two subscriptions in Unacademy. First one is a plus subscription. Plus subscription is the basic plan. Next one is iconic subscription. This is very important one. This is the next level of the basic plan, and it provides personal coach to you. In both the cases, there are commonalities. Your classes are taken care by the India's best educators, and interactive live sessions are available, interactive live classes, and the structured courses and PDFs they will provide, and live tests and quizzes. And one more important thing here is, in live tests and quizzes, see this, once you joined in iconic plan, what are the tests and quizzes you've written, the test was properly analyzed by our personal coach who are allotted to you. Okay, based on that analysis, they will prepare a proper study planner to you. By analyzing your paper, they will note the points where you are strong, where you need much preparation, where you are doing mistakes. Even though you prepare the topic, okay, due to some constraints and some problems, students are doing little bit small problems in examination. But in GATE examination, the small problem is enough to lose nearly 5 to 10 marks. Okay, so they will note down that mistakes what you are doing in examinations. Okay, and they will inform that one to you. Okay, they will make a proper planner to you, and every time they will inform you and they will intimate you where you are doing mistakes. From the knowledge of that information what they forwarded to us, we can take care of not doing such type of mistakes. So you are not doing such type of mistakes, in this sense you are going to gaining 10 marks in your examination, no doubt at all. Okay, you are not going to lose any mark by mistake. Now, and proper study planner they will prepare. Okay, and proper study material also they will provide to you. from the knowledge, by following these two effectively, one can definitely crack the examination. That is the intention to provide personal coach. Okay, what are the positives from your in your side where you are doing committing mistakes? Okay, so everything is prepared by properly planned, prepared, and your study plan is prepared by personal coach. Okay, just to following him, by following his planner, a student can definitely get the better result in their examinations. Okay, now we have to now we are moving to the cost for each and every plan. Now in plus plan, this plus plan is available for different subscriptions. 1 month subscription is there, 3 month subscriptions is there, 6 month subscription is there, 12 month subscription is there, 18 month subscription, 24 month subscription. Okay, so different subscriptions are available, but we are recommending a student to take minimum of 12 month subscription. As a faculty, I recommend students to take minimum of 12 months, 1 year subscription. Then only a student can enjoy the subject, complete his course by its cost is actually 30,250 rupees. By using my code VROW10 during subscription, you can get that by 10% discount with a cost of 27,225 rupees only. 27,225 rupees only. Okay. Now, if you compare this cost with the traveling expenditure for a year, if you join somewhere at outside, if you join somewhere for taking the training for GATE, okay, there you need to travel from your home to that location throughout the year during public holidays and weekends. The traveling expenditure for that throughout the year is more or less is 20,000 plus. Now the cost of this one is just 3 to 4,000 more than this amount. Okay, just by spending the amount of traveling expenditure, you can get the benefits what you are getting by going there and sitting the class in that. The same benefits you are getting by sitting at your home itself. If you want to say strictly, more than that you are getting. More than that benefits you are getting. Now the beauty here is EMI options are available here. Now we are moving to Iconic plan. In Iconic plan only two subscriptions, 1 year subscription and 2 year subscription. The 1 year subscription cost is 50,250. By using my code during subscription VROW10, you can get it by 45,225 rupees only. Okay. So here we are providing personal coach to you. Now this amount is close to the amount what you are paying to the tuition fee as a tuition fee to institutions. So by paying this much amount, you get more benefits. No need to travel anywhere. Okay, just by sitting at your home, you can get more than that benefits. So my dear students, please don't waste your time. Okay, time is valuable, and whatever the thing is happen at outside, your learning process should continue. Okay, so please think once and enroll today in our Unacademy. Thank you. Now we are moving to our topic, today's topic, energy band diagram of biased PN-Junction Diode. Already in semiconductors we discussed energy band diagram of a P-type semiconductor and N-type semiconductor. Okay, without biasing condition and with biasing condition. With biasing in this sense, by applying some external voltage to that, okay, how that energy level is varying. For your better understanding, I am going to first define representing the energy band diagram of a P-type and N-type semiconductor. Let us first I am taking the P-type semiconductor. P-type semiconductor I am taking. So the energy band diagram of p-type semiconductor is, so this is the energy band diagram of a p-type semiconductor. This is the intrinsic Fermi energy level. Fermi energy level of p-type semiconductor is close to this valency band. This is the EC, EFI, intrinsic Fermi energy level. Fermi energy level of n-type p-type semiconductor. This is close to the valency band, maximum energy level of valency band. Okay, now this is the case for a p-type semiconductor like this. This is just p-type semiconductor. Now here what I am doing is, here I am going to biasing this p-type semiconductor. Let us take p-type semiconductor. Here I am taking, I am applying some external biasing. This is p-type. So external biasing I am applying like this, positive, negative, positive, negative. So from this it became positive this end, and this end became negative. So this is the direction of electric field, direction of electric field. Okay, now the energy band diagram for this one is like this. For a this is biased p-type semiconductor. For this, energy band diagram is like this, like this. This is intrinsic and this is Fermi energy level. So this is EC, EFI, EFP, p-type semiconductor, and it is EV, maximum energy level of valency band. So Fermi energy level is moving this side. So Fermi energy level is moving this side. Now the direction of electric field E can be written as, electric field strength E is dE by dx. dE by dx. It is directly proportional to dE by dx. So electric field strength is increasing in a direction, dE by dx increasing in a direction of dE by dx. So dE by electric field is directed from this direction to this direction. Okay, so your energy level also, energy also moving this side. Similarly, I am moving to n-type semiconductor. In n-type semiconductor, now I am taking n-type semiconductor. N-type semiconductor. For n-type semiconductor, we know that this is the energy band diagram, and here is somewhere close to conduction band Fermi energy level. EC, minimum energy level of conduction band, EFN, EFI, and it is EV, maximum energy level of valency band. Okay, the way how energy levels are bending in p-type, the same way dV by dx. Okay, electric field is changing in that direction, it is going to be changing. These are the energy band diagrams of n-type and p-type semiconductors individually. Now if you are going to move into PN-Junction Diode, PN-Junction Diode, in PN-Junction Diode what happens is, in PN-Junction Diode, your p-type and n-type semiconductors both are joined to each other. This is the PN-Junction Diode. Here is, this is P region, N region, and at junction we have a depletion region. In junction, at the junction we have a depletion region. This is the depletion region. Okay. Now I am going to representing the energy band diagram of this. This is the PN junction diode under open circuit conditions. Okay. So that means we did not applied any energy so far, any external potential to that, any external voltage we applied so far. Okay, simply it is open circuit. Now I am writing its energy band diagram. First of all, this is going to be a single silicon crystal, and from previous what we observed, in n-type semiconductor, Fermi energy level is close to the conduction band. This is the important point you need to be considered. You need to keep it in your mind. Okay, and in p-type, here is the, so just remove this because you may get confused. Later we have a separate problems on this. There we discuss in detail about this, about biasing. Now here, this is the in valency band. In p-type semiconductor, what we have is Fermi energy level is close to the valency band. Here is the important one. Here is the important one. Okay. Now, based on these two, I am going to representing the energy band diagram of a PN junction diode. Okay. So, see this. Now, it is, so first in p-type, first step here you have to follow is Fermi energy level, because this PN junction diode is formed like this. First they take the intrinsic semiconductor, just they place a mark on center, and one side doped with the third group impurity, other side doped with the fifth group impurity. Okay, fifth group impurity, other side doped with fifth group impurity. Then your junction is going to be forming. Okay, that means basically it is a single semiconductor. It is basically it is a single semiconductor. So once it is a single semiconductor, its Fermi energy level is constant throughout the region under open circuit conditions or under steady state. Now first I am going to draw that. So this is the Fermi energy level of a semiconductor under steady state. Fermi energy level of a semiconductor under steady state. Next one is, I am going to representing the, so finally this is the Fermi energy level in p side. This is the n side, so it is EFN, Fermi energy level in n side. Okay, now we know one thing, in p side Fermi energy level is close to the valency band, so it should be close to the valency band. Okay, sir. And at the same time, in n region it is close to the conduction band. Fermi energy level is close to the conduction band. This is the conduction band. Okay, now this is EVP, valency level at p side. This is the conduction band, ECN, in n side conduction band. Why? Because it should be, Fermi energy level should be close to conduction band in n side, and it should be close to valency band in p side. Now, so this is the valency band, conduction band in p side, similarly valency band in n side, that's it. This is the valency band in n side. So that means it is EVN and this is ECP. So conduction band in P side is greater compared to conduction band in valency band in N side. Similarly, there is a valency band is above the valency band in N side. And similarly, same variation takes place in intrinsic also. Intrinsic also. Now, how much that variation, how much it is that variation is already we defined contact potential. We defined contact potential. Now, this is contact energy difference. This is the contact energy difference. Contact energy difference it is, and the same amount is going to be, there is a variation of same amount in I naught also. Now that variation is Q times V naught. That energy difference is Q times V naught. Q times V naught. That is the variation. Q times V naught. So clear? Q times V naught. This is the energy band diagram of a PN junction diode under open circuit condition. Energy band diagram of a PN junction diode under open circuit conditions. Okay. Now I am going to taking PN junction diode and biasing it in a forward. Okay. Now I am going to, this is the open circuit energy band diagram of open circuited PN junction diode. Energy band diagram of open circuited PN junction diode. PN junction diode. Okay. Next we move to forward biased energy band diagram of a forward biased PN junction diode. Energy band diagram of forward biased PN junction diode. PN junction diode. Forward biased PN junction diode. Okay. Now see this. Now I am taking the diode. So this is PN junction diode. So this is the junction. So depletion width is approximately 0 in forward bias. Okay, and let us assume one thing. The applied voltage is not make the depletion width 0. Let us assume some depletion region. That means applied forward voltage is less than the V gamma. So applied forward voltage is less than V gamma. Forward voltage is less than V gamma. Cut-in voltage. Then a small depletion region is there at the junction. So P region and N region. But your junction is in forward bias. Don't forget that. Okay. Now I am going to its energy band diagram. Once you forward biased your diode, then the barrier potential is V barrier potential. V barrier is contact potential V0 minus Vf applied forward voltage. Previously there is a energy barrier difference of Q times V0 we have. Now it is Q times V0 minus Vf. So the difference is decreasing. Okay, but initially previously energy Fermi energy level is constant throughout the region, but this time that is not the case. There is a change in Fermi energy level on both sides. The difference of that between the Fermi energy level of n side and Fermi energy level of p side is Q times Vf. That is the difference between the two Fermi energy levels, Q times Vf. Now I am going to draw that plot. This is the valency band. This is the conduction band. Sorry, conduction band and valency band. Similarly, in this side, this is the in n side conduction band. In n side valency band. Okay, now here in p side Fermi energy level is somewhere here. In n side Fermi energy level is somewhere here. Okay, so this is ECP, conduction minimum energy level of conduction band in p side, maximum energy level of valency band in p side, and this is EVN, valency band, maximum energy level of valency band or valency energy level at n side, and this is ECN, and this is Fermi energy level on p side EFP, and this is Fermi energy level on n side EFN. Now here these are going to be joined like this. There is a difference. I am joining these two. Here the important point you need to be considered here is the difference between these two Fermi energy levels is Q times whatever the forward voltage you applied. So that means here I am applying a forward voltage. Forward voltage I am going to be applying to this. Forward voltage applying across the diode. Q times Vf. This is the energy difference between the Fermi energy levels on both the sides. And the difference between the valency energy levels and conduction energy levels is Q times V0 minus Vf. Similarly here it is Q times V0 minus Vf. Okay. Okay, sir. So this is the complete energy band diagram of forward biased PN junction diode. If it is reverse bias, what we are expecting is in reverse bias, applied reverse voltage is VR. In that case, the barrier potential became V0 plus VR. Barrier potential became V0 plus VR. Now, the difference between these two, the distance between this ECP and ECN is going to be more. It is increasing. Okay, the difference is increasing. Okay. Now, this is about your forward biased. Next, I am moving to reverse biased PN junction diode. Okay. So, reverse biased energy band diagram of a reverse biased PN junction diode. Energy band diagram of a reverse biased PN junction diode. PN junction diode. Okay, now just a minute. Now it means here, and one more see this. You may ask one thing, sir. Once I'm applying the applied voltage more than that, applied voltage more than that, we go applied voltage, forward voltage is, if forward voltage is sorry, if forward voltage is more than cut-in voltage V naught contact potential, then what happens? See, once both are equal, then this difference is zero. Now this is the energy band diagram. ECP, ECN. Similarly here also ECP, ECN. Okay, EVP, EVN. Now here is the Fermi energy level. Here it is the Fermi energy level. That is the difference. Q times VF. Okay. So that is the case. This is the case when both are equal. If it is more than, now it is increasing up. This is going to be decreasing. ECN, ECP. Okay. Now this is the energy band diagram. If EF is greater than EV. Similarly here also. That modifications takes place in the energy band diagram. Clear? Next. Now I am moving to reverse biased one. So this is our PN junction. So in reverse bias we can observe one thing, depletion width is increasing. So this is the depletion region width. Okay, and this is P region and this is N region. So this is the depletion region width. This is the depletion region width. Now here it is in P side. This is the conduction band. This is the conduction band. And this is the valency band. Similarly here in this side, this is going to be the, okay, just a minute. Okay, this is the conduction and this is the valency. And here this side, this is the conduction band and this is the valency band. Okay, that means this is the ECP and EVP. This is ECN and this is EVN. Okay. Now we need to place the Fermi energy level. So here Fermi energy level is close to the valency band. Here Fermi energy level is close to the conduction band. So this is EFN, Fermi energy level in N side, and it is the EFP, Fermi energy level on p side. Now the most important thing is how much separation, this one, how much amount of separation between these. Okay, now here the separation between these two is, here this separation is and similarly this value, this separation is Q times whatever the V naught contact potential plus applied reverse voltage VR you applied. So Q times V naught plus VR. Now at the same time there is a difference between the two Fermi energy levels. Now that difference is, Q times VR. Q times VR. That is the difference between the two Fermi energy levels. So like this you can draw the energy band diagram of a PN junction diode. Okay, now just, yeah, this is the complete band diagram, complete energy band diagram. Okay, so like this you can draw the energy band diagram of a reverse biased PN junction diode. Now here the separation between the two conduction energy levels, conduction band energy levels for p type and p type n type is increasing. Similarly between separation between the valence energy levels also going to be increasing. Okay, and two Fermi energy levels also separating. Now the amount of difference between the Fermi energy levels is Q times VR. Q times VR. Okay, Q times VR. Now just we go and solve a problem on this. Okay, so students please take a note of a problem on this. We go and do one problem on this. Right. So there is a PN junction. So where it is? Yes. See now, write down a problem on this. See, the problem is an abrupt PN junction made of silicon. See now, take the problem. Okay, an abrupt PN junction made of silicon an abrupt silicon PN diode An abrupt silicon PN junction diode has Na Na acceptor doping, sir, equals to 10 power 18, 10 power 18. So 10 power, so is 10 power 18. So 10 power 18 it is. Okay, I will write that. Next, 10 power 18 per centimeter cube, and on the P side and ND equals to 10 power 15 per centimeter cube on the N side at 300 Kelvin. So find the positions of Fermi energy levels on P side and N side. Find the positions of Fermi energy levels on P side and N side. Sorry, sir. So this is the problem. Okay. So here it is 10 power 15 per centimeter cube, and it is a 10 power 18 per centimeter cube. Yeah. So this is our problem. So you need to calculate the Fermi energy level position on P side and N side. Yeah. See, now I am taking the PN junction. So this is the PN junction. So this is P region and N region. They given amount of Na doping here is 10 power 18 per centimeter cube, and Nd is 10 power 15 per centimeter cube. And one more thing, they given Ni also to you. Ni is 1.5 into 10 power 10 per centimeter cube. Ni is 1.5 into 10 power 10 per centimeter cube. Okay, now you need to calculate the Fermi energy level positions. Clear? Now I am dividing this one into two parts. In P side and N side I am separating both. Now we have an equation at P side in between Ni and valency energy level, between the Fermi energy level of P type material and the intrinsic Fermi energy level. That equation is EFI minus EFP equals to KT into ln of Na by Ni. This is the equation we have. Similarly, in N side, in terms of doping and Ni, we have a relation, that is EFN minus EFI equals to KT into ln of Nd by Ni. First I am going to calculating this. This is KT 25 milli electron volts. It is 25 milli into 10 power minus 3 into ln of Na 10 power 18 by Ni 1.5 into 10 power 10 per centimeter cube. Just to simplify this, it is 0.025 into ln of 10 power 18 by 10 power 10. It is 10 power 8. Now it is 10 by 1.5. It is 6.66. 6.66 into 10 power 7. So by simplification, it is 0.025 into 0.025 into ln of 6.66 plus 7 times ln of 10. ln of 10. This is 0.025 ln of 6.66. So ln of this one is 1.89. 1.89 plus 7 into ln of 10 is 2.302 something. Now just simplify this. 0.3 into 7 is 16.1 plus 1.89. It is 17.99 into 0.025. That is 0.449. 0.449 electron volts. So approximate value I am taking 0.45 electron volts. Just keep it. Now move to this side, n side. Now this is 0.025 into ln of nd. They given it as 10 power 15 by 1.5 into 10 power 10. So it is 0.025 into ln of, it is 6.66 into 10 power 4. So the same value 0.025 into, so it is ln of 6.66. So you get it as 1.89 plus 4 into ln of 10, 2.3. So it is, its value is 4 into 2.3, that is 9.2 plus 1.89, 11.09 into 0.025. Yeah, it is 0.277, 0.27 electron volts. Okay, that is the value. So we need V0 also, because the separation between the ECP and ECN is Q times V0. Q times V0. Okay, so that's why we need to calculate that also. Now, so that is Q times V0. So V0 why we need to calculate. So for that, see this. Here I am going to calculating the V0. So we know V0 is Vt into ln of Na into Nd by Ni square. Na into Nd by Ni square. See how I am writing this. It is Vt, V0 equals to Vt into ln of Na into Nd by Ni square. I am writing it as small n, small a, small a I am taking. Ni into Ni. Now we can write it as Vt into ln of Na by Ni plus Vt into ln of Nd by Ni. Now this Vt into ln of Na by Ni is nothing but a, this part is simple, EFI minus EFP plus, and this part is this one, EFN minus EFI. EFN minus EFI. EFI. So already we know the values of that, just add here. Now it is 0.45 electron volts plus this is 0.27. Now, so 0.45 plus 0.27. This is 0.72. 0.72 electron volts. So this is in electron volts, you get it by Q, you can write, because it is kT by Q. That kT value you mentioned, that EFI minus EFV is E by Q. So by Q. Now you can write this is in volts. In volts it is. Now this is also, it also became volts, because I am taking this VT this side. Then it is volts. Okay. Now, so see this. Here we have just a small modification here I done. Here we have an expression. Here KT, but here we have KT by Q. VT means KT by Q. It is KT by Q. Okay, so KT into ln of this much is, KT into ln of this much is this one. By Q we have, by Q here we have, just I added that Q to this. Now, so far we know we got V naught also. Now I am going to complete energy band diagram of it. So complete energy band diagram. So first diode is open circuit. Let us take, this is the separation. Okay. Like this. And this is the P side and this is N side. Now, so far what we know is, I am going to writing, first of all this is under open circuit, because they did not mention any information related to biasing. So, and that too, PN junction diode is a single semiconductor, single type of semiconductor. In that aspect, I am going to taking a Fermi energy level is constant throughout the region, equal both these sides. This is the Fermi energy level. So at this end, it is the Fermi energy level of P type, P side, EFP, and it is EFN. Okay, and next one. So we know the values of this with respect to intrinsic. So with respect to intrinsic semiconductor, its value is EFI minus EV we calculated, that is 0.45 electron volts. This is EFI, and this value is 0.45 electron volt, 0.45 electron volts. Similarly, we calculated intrinsic Fermi energy level this side, that is a 0.27 electron volts. This is a 0.27 electron volts. This is the EFI. Okay. Now, this is going to be separation between this, that is Q times V naught. Q times V naught, that is 0.72 electron volts. Okay, now I am going to, the next one is EV. So EV is, compared to this, it is 0.55 electron volts. Why? Because this is This is approximately EIFI is midpoint of energy gap. That's why somewhere here is your valency band energy level, and somewhere here is EFN. Now it is close to the conduction band. Now somewhere here your valency band. So this is, it is ECN, EVN and ECP, EVP. So I am joining all this, joining these two. So joining these two. Now this value I want. So its value is Q times V naught. We know that Q times V naught, that is 0.72 electron volts. Similarly, this one also 0.72 electron volts. 0.72 electron volts, because it is QV naught. Now I want this one and this one. So the thing what we know here is this one, we know that it is a 0.55 electron volts, and from here to here it is also a 0.55 electron volt. 0.55 electron volts, we know that. Now 0.55 minus 0.45, it is 0.1. So this is 0.1 electron volt. 0.1 electron volt. And similarly, this is 0.55 electron volt. 0.55 electron volt, and it became 0.55 minus 0.27, that is 0.28 electron volts. 0.28 electron volt. So and the remaining is this one. This is 0.55 electron volt. Okay, so this is the complete energy band diagram of a PN junction diode with given amount of doping Na and Nd. Now in examination you can expect any problem on this, any data. They may ask with respect to position of valency band on p side with respect to Fermi energy level of this one, EFP, okay, or with respect to ECN. See clearly, see carefully. Now they may ask this one, EFN, see this, EFN and EV. They may ask this one, separation. See, with respect to ECN, Fermi energy level is 0.28 electron volts, and with respect to this Fermi energy level, EVP is 0.1 electron volt. Now the separation between ECN and EVP is 0.28 plus 0.1, it is 0.38 electron volts. So once you are familiar with this diagram, or once you are familiar to draw the energy band diagram like this in detail, okay, then you can represent whatever the value they want. Easily you can provide that value to them. Okay, so my dear students, whatever the procedure we followed in a semiconductor, the same procedure here also I followed. Okay, just from the knowledge of how to draw the energy band diagram of a open circuited by a PN-Junction diode and biased PN-Junction diode, I draw this diagram, and from the calculations whatever the values I got, I placed here, and based on the standard values 1.1 energy gap, because they given it is a silicon. For silicon, energy gap is at room temperature 1.1 electron volt, and EFI is the midpoint of the energy gap approximately, so you can take it 0.55. From EFI to EC or EV, you can take it 0.55 electron volt. From that estimations, I calculated all these values. Now in examination, they may ask anything. What is ECN minus EVP? See, what is ECN minus EVP? Okay, or ECP minus EVN, they may ask. So this one to this one we need. So from here to here it is from here to here ECP to this value is 0.55 plus 0.45, 0.95 plus this value is 0.27, 0.55. So this value is 0.95 plus 0.27 plus 0.55. This is the value. Okay, this one. Like this, you may expect any question. They may ask any relation. So my dear students, you should be in a position to answer anything. So that's why, that is the intention behind the drawing the complete energy band diagram and to represent all possible energy levels. Okay. So please, my dear students, try to solve the problems in this model like this and get benefit when they was given in examinations. And now I am thanking to one and all for spending your valuable time with us. Okay, don't forget to use my code VRAW10 during subscription. By using my code VRAW10 during subscription, you get 10% discount. And please click on this bell button to get the notifications. Join our Telegram group to get the latest updates of our upcoming videos. And don't forget to subscribe. Okay, and please give your valuable comments on YouTube to strengthen ourselves and to provide a better information and quality information to students. Okay, now I am thanking one and all for spending your valuable time with us. Okay, and I am once again welcoming you all to India's largest online learning platform, Unacademy. Thank you. Thank you.